Today we're going to demonstrate how you can use the parametric utility in Lorentz to vary the excitation level in a pair of quadrupole magnets and study the effect of this on beam spot size. So here I've opened the parametric setup dialog box, and you can see we have a single parameter defined. We're scaling the volume currents of the quadrupole magnets. We scale them from a value of 0 to 1 over 51 steps. Now I run this parametric already, and this video shows the results. Here's the first step where there's no excitation current. The beam maintains its original circular shape throughout the simulation, and as we increase the excitation level of the magnets, you can see that the beam becomes distorted. It's being compressed in the Y direction and expanded in the X direction. If we increase the excitation level further, we eventually achieve a focus in the Y direction. And then as we increase beyond this level, we now have a divergence past the focal point, but we're also getting more of a compression, getting refocusing due to the second quadrupole. And you can see this is distorting the shape of the beam, and the spot size will vary along the beam axis. Now we can set the parametric utility to automatically record the spot size variation. I've already done this for 3 points, right at the emitter, and then midway between the two quadrupoles, and then at some distance beyond, slightly beyond the second quadrupole. Now I'll add 2 more spot size post-processing options. So we activate analysis, spot size on user axis, and the program is asking us to specify the distance along the axis. So for the next point, the distance is 4.5 meters, and we'll sample beam number 1 for 100% of the current. So that's added a new spot size calculation. We'll add the last one now, and this one is at 6 meters, once again beam number 1 and 100% of the current. So now we have our spot size variation at 5 different points along the beam axis. Now I've already run this parametric, and we can look at the results in the parametric results table. You can see that the table records the spot center and the spot size for each of the 5 post-processing settings. And we'll graph these results now. We'll graph the first spot size right at the emitter, and this opens up an autograph window, and you can see at the emitter there's no variation as you'd expect. Next we'll look at the spot size variation midway between the two quadrupoles, and you can see that there's a steady divergence as you increase the excitation level. Then just beyond the second quadrupole. Now here again we see an increase, but the increase begins to drop off at the higher excitation levels. Then at 4.5 meters, now I'm going to hide some of these other graphs. So the spot size at 4.5 meter initially increases with excitation, and then at full excitation it returns to about the same level as it originally was at the emitter. And finally we'll look at 6 meters. Now this has the most interesting effect of all. When we increase the excitation level, the spot size increases to a maximum, and then it decreases to a minimum value. That gives you the optimum minimum spot size. That's at about 90% of the current level. And beyond that, the spot size diverges and begins to increase again.